Right, I'm going to maximize my screen here. All right, so this is my build update number 3, I think. And for anybody watching this video after our meeting, you can go to the URL yakcollective.org/project/yak-rover to learn more about this project. Okay, so a lot to cover today. So I want to spend a couple of minutes on project management for the next cycle. So next 6 weeks or so, then the rest of it is pieces of my update on my build. So let's get right into the project management. Okay, so today we are kicking off the 4th cycle of meetings. As you know, we have like basically an 8-week cycle because there's 8 of us covering various points. And yeah, you can swap your scheduled slots as usual if you have issues with it. But this is the order we've been going in. So today is me, August 9th is Eric, then Victor, Anuraj, Meyer, Rhett, Yasha. And Yasha will have, I guess, another special topics. And then September 20th, that'll be the start of the next cycle. And that's when I think we should really like do a strong finish, so a little bit on that. So I don't want to spend too much time on project management today because I think we're kind of like in the flow of getting things done. But on September 20th, we should plan on having a major project management meeting and plan like a strong end to the year. So we have a lot on the agenda. So we have to plan and do some sort of significant public event, a workshop or a school or something. We need a public demo, perhaps interactive, of showing off of whatever outputs we have. We've kind of got a stillborn website that we need to build out. And I think it would be time to do some PR. We'll have stuff to show, so it'll be good to do PR and maybe recruit new talent and basically finish as strong as possible so we can set up 2022 for the most ambitious year too possible. So I think this is all for the next cycle. But for now, let's just sort of table this stuff and keep discussing asynchronously during our regular meetings as well as on Discord and sort of focus on it in the next cycle. This cycle, let's try and get as far as possible so we have like a lot of raw material with which to like do a strong finish, right? So that's my 2 minutes on project management. We can talk more if there's time at the end, but let me dive into my build update. All right, so if you remember how my build started, I started with a design study, like a very simple version of a rocker bogie 6-wheel just to get some intuitions on how this works. So this was like super primitive. Like I had not built anything in like 15 years and it was like really crappy. Like you can see, instead of a proper hinge, I had a bent nail over here. And I tried to initially make an axle out of bent paper clips, but that was proved to be too janky. So I at least bought some rods and made a real axle. And I've ordered my first actual part besides 3D printed filament, which was some M3 nuts and bolts. So that's where I started in January. And how it went, Jan to March, I did this design studies. Then I started scoping for parts, trying out various things in April. If you remember my second design update, I was still thinking of using the TT motor, and that's when we had some discussions, and I think Yasha recommended the N20 because I was not aware that the N20 small motor came in multiple gear sizes. So that turned out to be a good choice. So I made the switch. I learned about turnbuckles. I built this little mechanism for trying out how the turnbuckle differential bar works. So all this was how it was going till May. And sometime in April, I was doing a lot of shopping all along the way. So a good way to track state for my build, since it's a sort of from scratch build, everything kind of build, the bill of materials is actually a good snapshot of project state. So this is what it looked like in April. You can see a bunch of interesting things here. Towards the lower right, there were like a couple of sample ball joints I was going to use. I only had the one N20 motor, but this was I think 24 reduction motor, so one of the fastest N20s. And later I switched to a very slow, extremely high reduction motor. It was a 1:298. But okay, so this was where I was in April. Okay, so now we get to how it's going. So I've kind of split my project into two parts because the mechanical part was so complex. I realized if I waited for the mechanical part to be done, I would never get to the electrical and compute. So I decided to build the simplest mechanical thing possible just so I could get to the testing of all the electrical components and compute. So going with my naming scheme, since my main build is called Nature is Murder, I call this accessory before the fact. So an accomplice before the murder. I'm very pleased with that name. But it's just a single piece body. Instead of 4 drive wheels, it has 2. It still has 4 steering servos like the main build. It has 2 passive wheels. But the main thing is the body is just one piece, a single 3D printed piece instead of like about 25 for the main build, as you'll see. But even that ran into problems. So the first chassis I built, kind of just winged it and printed it. And then I realized I forget what they're called, the riser strut-like things. What are they called? There's a specific word for them. Anyway, I made them too.
Screw boss.
There's a separate word I'm forgetting. It's not screw boss. Standoff, yes. So standoffs. So I had these integrated standoffs that I designed, but I forgot to measure the battery. I kind of just eyeballed it. Turned out to be too low. It wouldn't fit. So then I had to like redesign, as you can see on the right, and that was big enough to shove the battery underneath because I wanted the battery below for a lower center of gravity. This is, let me try and move this over. This is the bill of materials for the accessory before the fact build. You can see at the lower left, you've got a couple of N20s. These are the 298 reduction ones. These are the sort of components of the wire harness. You can see there's like 1, 2, 3, 4, 5, 6, 7 3D printed parts here. But totally there are 16 mechanical parts, 36 fasteners, 6 motors, 1 computer, 1 battery, 7 interconnect cables, but not counting the 4 integrated ones for the servos. And there's 4 to 8 connectors I still haven't like figured out how to design. So there's like, this is, I would say, a 90% complete BOM because I haven't locked down some design decisions. Oops. Okay. So this, after printing and everything, it took like a whole day to build and it looks simple, but lots of subtleties. This was weirdly more challenging than I thought for kind of stupid reasons, which I should have really anticipated. But this is, well, I got it done, so this is proof. But okay, so the most complex step was basically, this is the SG90 servo. It just goes through a hole affixed to the main chassis, and then it is bolted onto the motor fork. This is actually the passive wheel fork with a horn. So this can't be that hard, right? So look at all the things I managed to get wrong. So in my initial design for the little strut, I kind of forgot that I actually need access to the bottom of the servo horn to actually screw it onto the servo motor. So I didn't design that into the print, so I had to actually drill holes afterwards. But that turned out to be kind of useful because I next discovered a problem of it was really hard to hold this servo horn down on the part, like clamp it firmly enough to like fasten it. But now that I drilled the hole, I could just like hold it with a bolt. So that turned out to be a dual purpose thing. So that was kind of my work holding solution. So visualize assembly before printing is like, it's kind of an obvious thing they teach you in mechanical engineering school, but it's easy to forget to do something as simple as you need a hole to like screw things in. Another one, so the servo motor and horn, it came with a couple of like screws, which it said it was like self-tapping screws. So I assumed I could like just shove it through the hole and screw it in. Turns out it didn't want to really go into PLA. PLA is stronger than it looks. And what happened was, as I was trying to, it's a very small, delicate screw. It's like, I think M2 or something. So as I was turning it, it was just pulling up the horn. It was not penetrating the 3D print. And I managed to strip the screw head, as you can see on the right. So basically, then I had to pull this off, drill starter holes, and then I was able to fasten the horn. And I kind of had to use like needle nose pliers to tighten the screws because I'd already ruined the head. So lesson is put starter holes and marks on print everywhere if you can. Lesson number 3 from this initial build. This actually initially worried me, and it turned out to be easier than I thought. So I bought these 6 wheels or toy wheels basically for the N20 motor. As you can see, it is cut for a 3mm D shaft over here in the middle. And I didn't know how to do the passive roller wheel with it, but it turned out I could just shove a 3mm shaft in and it rolled pretty well. So this is a good enough solution for the accessory before the fact, because this is not a rugged design meant to actually do roving. It's just meant to like test the motors and electronics. So it's good enough for this. But for NIM, the Nature as Murder main build, I'll probably be designing separate passive and active wheels with like the proper bushings or bearings. This was a fun one. So for the passive strut, so that's this one, to hold the wheel between the 2 parts of the fork, I wanted to get the size exactly right. And I wanted basically a compliance interference fit. So shove a rod in between. This is not a through hole. So I just wanted it held in between the 2 ends of the fork. And I thought a clever hack would be to cut a toothpick approximately to size to make sure it like fits directly in the fork. And that turned out to be about 27mm. And then I took my 3mm rod and hacksawed it. Turns out steel is much stiffer than wood. So when I tried to shove it into the fork, it was like far harder than it needed to be. So interesting little thing to learn. Like when you use one material to test how another material will behave, you got to take even these little details into account. Another one. So I was thinking of 2 designs for the drive wheel strut cap. Is it kind of obvious what this is? So this is the fork for the drive wheel. And can you guys see my cursor? Over here, so the little arch at the bottom of the fork, that's where the N20 motor will go. And something needs to hold it in place. So I was thinking of these 2 designs. One is just a plate that bolts on, and the other is this end cap. And I want to like minimize fasteners as much as possible, do things with interference fits, use the compliance of the material to make the fit. So I made that red one initially, exactly to size. Or I think I put in like 0.5mm tolerance. But it turns out 3D printing is just not precise enough. So then I experimented with a bunch of tolerances, 0.5mm, 1mm, 2mm. None of it worked. Then I thought maybe one way to hack it is cut a slot. So I took the original one I printed and cut a slot down here to create some flexibility. And then it turns out that I didn't actually need to screw around with the tolerance. It just fit, just creating the geometry. So basically design a slot to amplify the natural compliance, and don't try to solve it with tolerances in an imprecise fabrication medium like 3D printing. Like you could probably do it, like I would say probably not PLA, but PETG with like the right tolerances for printing. You could probably get this compression fit without the geometry, but geometry is easier. Okay. Another fun learning. My battery cable turned out to be extraordinarily short. It's just 2 inches. So initially I had the battery oriented the other way around, like aligned long way to the chassis. Didn't actually get around. So I had to orient it this way to fix it. Now I bought an extension cable and it can be like configured properly. So, okay, so that got built. Any questions? Thoughts on the fabrication lessons and design stuff? All right, Beagleboard Blue. So I have this sitting around.
I'm trying to imagine how these translate into problems we have with software, and I'm still,
I'm sure there's equivalents. Like lots of things look like they work in CAD, but you fabricate them, all sorts of little problems crop up. So one of I think the reason I like documenting these, and I think you've all seen my Twitter thread where I like keep a running commentary on these, including the most minor looking things. It's like nobody tells you these things, but these are the things that you find the hard way. And if somebody had told you, you would like save 2 hours on design, 4 hours on like a failed print, and then redesign and reprint. But it's like there's too many of these little details to like, I guess, capture and explain. But I'm trying to like capture the ones that are at least like funny. All right, BeagleBone Blue. This is my weakest point embedded programming, but I got somewhere. So it's basically a BeagleBone Black, which is their more famous board with an integrated robotics cape. So cape is their equivalent of a hat or a shield for Pi or Arduino. They all seem to come up with their own names. So initially I thought battery management would be tough. But here, thanks Yasha again, he took a look and turns out that the onboard battery management is actually really good. So you don't need anything special. It does the balanced charging of the LiPo battery. It does, it has power indicators for the LEDs. It does basically everything. But I think if you wanted to use like an RPi, you'd need a special breakout board or a hat to do this on an RPi. So this is, I guess, the main advantage of the BeagleBone Blue. It does all this. I did a basic power budget. I think under nominal conditions, my power draw should be about 2.5 amps. If everything is going all out, like all the motors are stuck at like stall condition and it's climbing a heavy, sticky slope, it can go up as high as 4 amps, probably 4.5, I think. And that'll exceed the limits of what the BeagleBone Blue can deliver, I think. And it'll also exceed the limits of the battery I've chosen. But I figured that's a good problem to have because all rovers have power management problems. So let's face it and see how that works. And one issue with this board is the only way to do a proper camera is USB. Like it's got a bunch of other ports, but I talked to some people, none of these are suitable for cameras. You get like, I think some really primitive cameras that can hang off a UART, but basically USB is it for camera, which means you're using up the single USB port for camera. Unlike the RPi, which has a dedicated camera slot, here RPi is actually really good for other stuff. It has like 4 USBs, I think, and separate camera, 5. Okay.
No, not 5. I just want to comment.
Oh yeah, go ahead.
I connected a hub to my 1 USB port. We have 4 or 5 USB ports, and it's not enough.
Oh, okay.
It's also they're very difficult to access. You said that your battery had short cables. Each and every one of the USB devices you have, the cables might be too long or too short, or the problem I had, the connector that came with the device was too long and too stiff. So when I tried to connect it to the port, it banged into the body or interfered with the other connectors. So I bought a hub and attached it, and now there's room for everything and there's no distance problems.
Okay. Yeah, I'll have to keep that in mind. If I do end up needing more BeagleBone, USBs, that's one way to extend. But just for those of you who haven't looked at the Blue in particular detail, it's got 4 edge bridge motor drivers. So like motor control is taken care of. You don't need special motor breakout boards. So that's at the lower left of or lower right. Just above that, it's got 4 quadrature sensors. So my N20s each of them has an integrated Hall effect sensor. So each of them will be bringing out 6 cables. You've got 8 servo motor outputs. I'll be using 4 of them. So that leaves 4 spare for like, payload stuff. It's got the battery management, like I said. What else? It does have a bunch of bus options. And I was thinking I'll do I2C maybe as a sort of stretch goal for a bunch of extra sensors or LEDs or something. But right now, I'm just doing like direct cabling for everything. So that's the BeagleBone Blue. I had trouble getting it going. Yeah.
So a quick question. What is the difference between a BeagleBone Blue and black?
So BeagleBone Blue, like I said, is just the black with an integrated robotics cape. So cape is their word for the RPi hat type thing. So I think physically, if it were done with a black plus a cape, this would be twice as tall and basically 2 boards. And it would be like a physically more complex thing.
Okay, thank you.
All right, starting up, my Mac runs Catalina, and it turns out that all the drivers for the BeagleBone Blue don't work with the Catalina. So if you want to like start up Wi-Fi and connect to it, I did online research. Nobody has a good solution. By the way, there's kind of poor documentation and details in general for the BeagleBone Blue compared to ARPA and Arduino. It's a much, much smaller ecosystem. And even within that smaller ecosystem, the blue is its like most obscure board. The black is much better known. But still, it's pretty decent. I found what I needed. They do have like a full robotics library that's been refactored. So I had to like hunt around for the new version and install it. But eventually I did get it going. So I had to use my wife's computer, which runs High Sierra. So that the drive was installed, but I can't keep borrowing her computer. So I've decided I'll probably do like an ARPA tablet computer as the command module for this rover. It seems simple enough. The way this works is you SSH in through this Cloud9 thing that AWS has. So it's like cloud-based. For some reason, that's how it's set up. I haven't like really dug deep into how flexible this is. But you set up basically a web server, you go through a web browser and log in, it gives you a shell, you do the usual Unix things. I downloaded the repo of the robotics control and I got the Blink working. So this is a little messier and I can tell it's going to be painful compared to like Arduino or ARPI, but it doesn't seem too bad. And the advantages you get with all the robotics control, I think it's worth it. But anyway, that's all I have for BeagleBone. I'll probably have a lot more to say about this piece of the build next time. All right, so this is where I think I've made the most progress. The actual build of the main Nature is Murder mechanical design. And I'm trying to be smart here and do as much as possible in the CAD tool. So I have to like do minimum iteration cycles of print, redesign, and stuff like that. So I'm actually putting a shit ton of effort in this. So just to give you sort of a quick idea of like the boundary conditions here, there's 4 major large physical components that sort of constrain the design of everything else. So you've got the board itself with its like constraints of how big it is and where it needs to fit. You've got the ball joints, which are the most complex linkages for connecting the body to the rocker bogie side mechanisms. You've got the battery, and then you've got this turnbuckle linkage that I bought from a hobby thing. So let me escape this and switch to Onshape so we can look at that. All right, can you guys see my Onshape dashboard? Okay. All right. Honestly, I'm feeling proud about this. Like this is the most mechanical engineering I've done since 1997 when I got my mechanical engineering degree. And looking at what I've done here compared to like what it took to earn that degree, I feel like almost like a fake. Like actually building a fairly complex real thing is like so much more work than like just hacking out like a term paper project level stuff. And back then, of course, AutoCAD was primitive, parametric design was new, solid modeling. The first solid modeler I used was an internship at a robotics lab in Bangalore in 1996. So this was a defense robotics lab. And we used Pro Engineer and Ideas, the very early versions. And my actual mechanical engineering drawing classes were all on like 2D like pencil and paper, like actual drafting with a T-square and like a drafter. And then we did like 1 semester of two-dimensional AutoCAD with like a little exposure to 3D AutoCAD circa 1994, extremely primitive. And this is like, honestly, a beautiful thing. It's like a pleasure when you compare it to what you used to be able to do back then and how crappy it was. This is like amazing. But okay, let me show you. I'm going to switch to my other mouse since my horrible Mac trackpad is bad for this. All right, so this is actually a fully assembled kind of thing, and this was a bitch to assemble, frankly. So let me increase the size. Is it big enough for everybody to see? Okay, so let me just give you a little overview tour of the features. All the joints are live and active, and I'll give you some highlight details. But let's zoom in on a couple of interesting features before I show you some pieces. Okay. The overall body construction, all the red parts are going to be 3D printed out of 3D or red colored PLA. The silver bits are aluminum tubing. Let me see if I can grab one. So this is 1/2-inch aluminum tube, which I plan to like just cut into like the right members. And all these, this entire mechanism is built out of like press fit. So I'll show you some of the components. Let me actually see if I can. I'm going to switch back and forth. Let's see. So you can see kind of the logic of how I did this. So this is like a bunch of these struts are like pieces of aluminum cut to size. Then you've got all the connector parts are things that look like this. And a couple of things I want to point out, and this is kind of the advantage of doing the accessory before the fact build. So the trick I discovered with like compression fitting the cap on top of the motor end thing, I'm reusing it here. So little slot here that will hopefully make the compliance work. And this will just shove into the aluminum square member. So this thing should just fit into this, okay? And
you were doing anything to increase the friction between the plastic and the aluminum?
I'm hoping compression is strong enough to do the job, but if not, the two options are, one is to drill a hole and use bolts. Nuts and bolts are bad for this, so I might use something called a pop rivet. A pop rivet is this thing you can shove in from one end and fasten from just one side. But I want to avoid that because that's basically irreversible assembly, because one of the things I'm going for in this design is to make it as sort of reversible modular as possible. So I hope the compression fit will be tight enough to hold for like light roving, but loose enough that with like, a pair of pliers, if I compress it and pull it out, it just comes apart. But if not, we'll see. So there's some options. Like I can do these sort of push tab kind of thing, like have a hole through which like a little tab pops out, things like that are possible. But I'm starting simple, just a simple compression fit.
And what about having a locking screw? The reason I'm asking, the robot shakes, it jumps around, and these friction fittings can move.
I think from my experience with the accessory before the fact, it's pretty tight. I think it's not going to jar loose if I get it right. But if it does, my initial plan is to just actually make it tighter, like reprint the part with like a narrower slot or something. So try and make friction do the job as much as possible. But if not, like one extreme solution is just glue. Like once you've got like the trial assembly done and the wire harness in threaded properly, you can just glue it together if you don't intend to take it apart. Let's see, a couple of details. If you look here, all these joints, by the way, are 3D printable with no overhangs. So they can be 3D printed without too much complexity. There's a couple of exceptions, but mostly they can be easily 3D printed. Okay, so this, as you can see, is a little hole. So I've designed this so that where the aluminum tube fits into any of these parts, a little gap is left, and this is for threading the wire harness through. So for example, this is a drive motor, right? So from this end of the N20, there'll be 4 wires coming out for the Hall effect sensor. It'll go into this, and then it'll thread into the tube from there. And then when it comes out, let's see, this is kind of, I'm going to hide this. I'm going to hide a lot of things because they're kind of getting in the way. Okay, so you can see the logic, right? The wire will thread through here, get into this tube, come out of this gap here, and then go to the board. Same thing over here. It'll come in through this tube, come out through this one, go up into this one, come out through this hole, and then go to the board. So I'm hoping that the portions where the wire harness is exposed and sort of open to, like, getting damaged or cut or weathered are fairly limited, only around the moving hinges. And the reason even this has to be done is that this is too compact. This whole rover is going to be about the size of a shoebox. So there's not actually enough room to thread all the wire completely internally. And like, you could make the joints more complex so that everything is inside. But at some point, that'll, I think, make the size larger or the design way more complex. Okay, so that's how the wire harness is going to work. What else? Okay, so that's the main chassis. And you'll have the beagle bones sitting here. Okay. And oh, by the way, all these little things you see, they're mates. So mates and mate connectors. So these are how, like, the different parts are joined together. Some of them are active and they're like revolute joints or like hinges and things like that. Other things are fixed joints. Let me hide all of them because they kind of, and if you look on the left sidebar, you'll see just how many there are. There's 42 mate features already. Can you see on the left sidebar? So there's 42 mate features. And I don't know how many parts. I've lost count at this point. Let me hide. Okay, so this is the top view, and this part that I've highlighted is basically the payload deck. And I have a couple of thoughts on this. One is, this is likely just replaceable. Like, if you want like a payload deck that can do camera, you'll put on a camera deck. If you want one that has a little manipulator arm, you can put that on. That's one way to do it. Another way is to like add a few more holes here and have that, like, sort of have a landing deck on front that can be bolted on. Same thing in the back. In the back, there's a little bit of room. Sorry, still. So over here, this deck is basically there to hold the differential bar pin joint, but there's also room here. I could attach or extend this so that basically what you can, if you imagine, both the front and rear decks can be like expanded to as much is allowed by like mechanical stability and geometric interference. So within those constraints, I think the motors are powerful enough to actually move quite a big load. So it's actually just geometry that's constraining it. So if you have the right stability balance and geometry, this will work. Okay. This is obviously the most complex mechanical part. That's the differential bar. It's connected through these turnbuckle linkages to these rocker hinges. And I'll tell you a little story about that, but let me just show you how that'll move actually. I'm going to move it a little bit and you can see. Oops, I'm moving the wrong direction. Okay. Can you see the mechanism moving? So this is actually already pretty much ready for, with a little bit finishing touches, this is ready to import into an animation tool, and it could be put into a simulation program. So obviously this would be for like a very high fidelity mechanical simulation for things like, dynamics, friction, is it going to fall, is it going to topple, that kind of simulation is what I have in mind. But simplified versions of this could be like, more mission level, how are you going to get from point A to point B kind of stuff. But this is fairly detailed. Let me show you a couple more of such animation things. Yeah. This Onshape actually allows you to do some animations. Let's hold on just a second. Hold on. There's a easy way to do this. All right, never mind. I'll show it in a simpler assembly or something. Wait, this is all attached. But yeah, you can animate these things. I'm still learning the animation features, but yeah, I can manually move a few things around. And this is a constraint solver, by the way. It's like this. It's got 1, 2, 3, 4, 6 ball joint linkages and something like 10 cylindrical linkages. And all these are defined in the assembly diagram. And when you try to move it around just manually, it'll actually try to do the constraint solving and move the whole mechanism around. So if let me try and illustrate how this works. Okay, this is not solving very well. This one should solve well. Yeah. So it tries its best to solve. It's not very good at it. So it won't always move the part you think is going to move. It might move everything else to like solve the constraint. Anyway, and it's very easy to get this horribly mixed up because it does not check for interference. And one of the limitations of Onshape I've discovered is it does not allow you to constrain ball joints by how much they can move. So a ball joint gets defined as a ball can just basically roll inside another hollow ball, which means, so this is where my fun story comes in. When I was initially trying to integrate the turnbuckles, I didn't get the length quite right. And when I created those constraints, it went crazy. It like turned this into a completely messed up pretzel, and nothing I could do would like get the whole assembly back in order. And eventually what I had to do was basically turn off the constraint of one of the ends of the turnbuckles and then sort of manually rearrange the whole rover to look right. And then sort of arrange the turnbuckles to the right length, reinforce the constraints, and then it was able to solve. And I think what was happening was when I initially assembled it, even though it was possible for it to actually get to the right sort of configuration, it was near some other local equilibrium of the mechanism, and it was going into some pretzel shape because it was not constrained enough in the design. All right, so a couple other things, let's see. Oh yeah, so this was the hardest freaking thing to design.
Does the tool impact the angles we see on the rocker bogie?
The what?
You know, on the rocker, it seems that there is an angle on that is going. You have the V shape for the bogie, and the rocker is, or the contrary. Could you show it again, please?
Let me go back there. Yep. So these are fixed angles. These joints, 1, 2, 3, 4, 5. So there are these 5 elements. I just lost all my highlights. Let me re-highlight them. So
yes,
1, 2, 3, 4, 5, 6 plastic parts that connect the aluminum things. Each of them has specific angles, and that's fixed. Initially, I was kind of trying to be more ambitious and making those sort of reconfigurable angles as well, but that got too complex. Like it was introducing too many angles. So now my plan is, even though I can sort of change it in the parametric design, I'll show you a couple of examples. Even though I can change it, the idea is just to keep it fixed for one design. And this is, by the way, very rough geometry. I've just roughed it out, and now I have to like do the projection on the flat plane and actually do the calculations and get the geometry exactly right so that the wheels all line up on the flat surface and stuff like that. So I haven't actually done the final calculations. This is a very rough, think of this as a topological design. So the topology is the topology is correct and the geometry is roughly correct. Now I have to get the geometry exactly right so that the 6 wheels are on the ground at the same time. The hinges are like, in the right nominal position. So that has to still be done. But yeah, all these are angles. So let me show you a couple of examples there since you were. Okay, so this is an example. Let me. So this is the first plan that then got projected out into the part. And you can see this particular part happens to have a 20-degree cant. And so all of them, there's like 4 or 5 angles I have to set, and that'll determine the overall geometry of the rocker bogie mechanism. And I don't yet have any intuitions of how the geometry will affect, like, the stability or how it moves or rolling stuff. I have poor intuitions, and I don't want to attempt to get it from first principles. So I'm going to try and get it roughly right, print it, build it, run it, and then start tweaking and seeing, all right, is this angle too much? Is it getting stuck in a rut? And then sort of finalize it, because I don't think I'll be able to figure it out first principles. Maybe somebody much smarter than me at geometry can do it. I'll have to do it by actually building this damn thing. All right, so that's this part.
Thank you.
Let's see, what else do I have? Wanted to show a couple more features of this. Let's see, div bar. That's the div bar. That's not that interesting. All right, turnbuckle. So this is an enormously complicated part. It's got, these two are ball joints. Each end is a ball joint inside like a ball-shaped cavity. So it's like this little ball with a tube shoved inside it that can move like a ball. I think I have one somewhere right here. Give me 1 second so I can show you a physical one as well. I think I showed you guys last time, but just as a reminder, this is what the physical one looks like. I don't know how well you can see it. Each of the ends revolves. These things, I don't know if you can see me moving it, but the little barrel-like thing moves. And the middle part, if you turn the middle, it'll actually unscrew and you can change the length. So it goes from about 66 millimeter to about 100 millimeters. And these two screws that connect to the middle, one is left-handed, one is right-handed. And that's because they're torsioned in a way where if you don't have that right hand, left hand configuration, it'll sort of get loose. These mechanisms were first designed for tightening cable-stayed fixtures. So like, a ship's rigging, if you have a sail rope holding the mast, and then at one end it's fastened to the deck, you'd have one of these mechanisms. And the reason it's this way is you can just turn the middle piece of it and it'll tighten and shorten the whole thing and tension the cable. So that's where turnbuckles were first invented. And now they're used anywhere you need kind of like a rod that you can shorten and lengthen after it's in place. And both ends have ball joints because you want to create a 3D kinematic linkage. And this was a serious bitch to get right. Like I could have found like a roughly equivalent turnbuckle from McMaster Car, which sells like high quality professional ones that are more expensive. These are some cheap ass things I found off Amazon, which are used in like hobby builds for RC cars. And maybe I didn't look hard enough, but I couldn't find a CAD model for this. But I didn't look too hard because I kind of wanted the challenge of just doing it myself. So I did it. I think I gave out at the 70% point. So these things, initially, I wanted to make them screw linkages. So you can, this is right now just a cylindrical constraint. So you can see over here the way it's designed. Let me actually, I can try and animate it. You can see the animation. It's very tightly constrained, by the way. Like once I discovered that the right length was about 55 millimeters, I made it like 57 to about 60 millimeters or something. Because if I didn't do that, the assembly solver would go crazy because it was like so much freedom. It would like give the rover enough freedom to wrap itself in a pretzel. But this, I just made it a cylindrical joint so it can rotate and move longitudinally, but it's actually a screw joint. So you have to constrain them, and you can actually do that. You can define a screw mechanism here. And what it does is it constrains the translation and rotation by the pitch of the screw. That made it way more complex, and I couldn't get it right. So I just gave up and said, this is not that important because it's only used for adjusting the length. And once you've adjusted the length, there's actually a couple of lock nuts here that hold it in that position. So you kind of don't care. So I didn't do the lock nuts. I didn't do the right and left-handed threads. So I replaced it with like a simple cylindrical joint. So this is the turnbuckle. Still not great because these things, they should have like about a 30-degree off the poles kind of like movement. But as you can see, it can go crazy. It allows you to like move it randomly and it'll like interfere with the other parts. See it. Can you see what's happened there? It's messed up. So because you can't actually define a constraint on a ball joint that says that, you know, on azimuth and altitude, it has this much angle capability, this is basically a ball inside a ball. So if Onshape tries to animate this too liberally, like you can, let's see if I can animate this, you'll see what happens.
You can't put a constraint that the cylinder won't bang into the red thing?
That's called an interference constraint, and I don't think Onshape can do that.
Okay.
Unless there's a way, I don't yet know. But let me show you. Yeah, this is how it moves. It's not the greatest. So there may be a complex way to do this, but typically at this point, you kind of give up on the kinematic level of CAD and you would take this into a dynamics package and kind of like do it in a different way. This is at programming level. At this point, you should be writing a script to like govern the constraint solver a little bit. So I'm not trying too hard for all that. Like there's a point at which doing things in software and CAD becomes too complex and you kind of do the simplified model on CAD and then the real thing is actually much better behaved. Like this thing is actually a much simpler part than the virtual one that's sitting on the screen. So it's like the judgment call of, I'm just going to switch to the physical design and iterate over there at this point. And if there's issues with the turnbuckle linkage, I'll figure that out over there. Let's see what else. And this took a while to do. Like I had to learn a lot of things. Like this is the interior cylindrical / spherical thing. I had to learn quite a few little tricks to learn to like draw these things in Onshape. So it was a lot of fun. So this was probably the most fun thing of this part of the design. But let's take one final look at the assembly and see if there's any other overview things you guys want to see. Let's see. Oh, one more thing I want to show. It may not be very super visible, but initially you can see that I have the middle wheels pushed out. And I have this vague idea that if I can get all 6 wheels to basically be able to fit inside a circle, so a circumcised circle or circumscribed circle, then if I have the wheel angles correctly, like a hexagon, basically, it should be able to rotate in place very smoothly. I don't think that's going to work out. It'll have to be too far out to do that. And I can make the body a little wider and I can make the struts a little shorter. But I think I'm going to give up on that and kind of like give up on rotating in place as a thing. It can still do it. The middle wheels are passive, so they'll drag a little bit. You can sort of do the 4 drive wheels at the right angles to create like a circle and then do like a circle. And then the middle wheels will kind of like do whatever the hell the passive wheel will do. You could do casters, you could do the omni wheels or something, but too complicated. I'm going to just give up on that maneuver for now in this build. So that's something to look at. And what else is here? I have left room for the middle wheels as well. These are passive wheels, but I could still put instrumentation in them. I could put an optical encoder on this axle and measure its speed. If it comes off the ground, it's going to go 0. So those kinds of things I can measure, and there's room for cabling to go through there to the main body. All right, so this is the mechanical design. So now I have to like refine it, get all the dimensions exactly right, make sure like it's actually fabricatable, each part. All those, you know, assembly constraints I have to think through, like is each of these actually assemblable? Like I just realized something, this stepper motor, I don't think it can be assembled in this position because the part that juts out below and holds onto the horn, I don't know that I can maneuver it into that hole. So that's something to think about. And if I go back to the real units, let's see. Oh, the SG90, I found CAD, some open source guy had done. let's pick this one. So these are the steering boxes. So that's the hole through which the servo motor steering motor sticks through. And if you can think about the assembly problem, the motor has to be shoved in and put in through the hole. And the reason, by the way, I'm sort of kind of belaboring these basic mechanical engineering things is because I'm actually interested in the research version of this problem, which is if you want to design for decomposability, scavengeability, remember my original research goal was scavengeability. If you have half a dozen of these rovers on Mars and one of the robots dies and the other robots want to use it for spare parts, you have to be able to take it apart and put it back together again. So that's like a much harsher mechanical engineering constraint than on Earth, where you can throw away things you no longer want. You can kind of do destructive dismantlement. You can do lots of other things, right? Humans are more creative. So that's kind of why I'm a little bit interested in like design for assembly in kind of a deeper sense. All right, I think that's it for my mechanical design. Any questions on this while I have Onshape open?
Very impressive.
Please, Mayor.
I just wanted to say it was very impressive.
Thank you. Yeah, question? Eric, you had a question?
Yes, I was. I'm also using a little bit Onshape since Joshua and you introduced it, and it's very interesting and a lot of things we can do with it. I wonder, so you talked about making simulations to see whether to study whether where the pressure would be and so on. Okay, and anything can be done inside Onshape about that. I'm thinking about you've chosen some angles, okay, but before building it, maybe we can have some ideas whether these angles are good in terms of will it break because of some payload. Okay, that's one thing.
Onshape
But
can't do that. So that would be dynamic simulation. So you'd have to put it into a different CAD tool. So I don't know what the best in class right now is, but yeah, you'd have to put it into a different thing and put like dynamic stresses, loadings, all those kinds of things. So that's something I definitely want to explore next year. But right now, actually, the easiest way to do dynamics testing is to actually fabricate the damn thing and like actually stress it. So that's what I'm planning to do, like actually build this and like, attach a spring to it and see how much pull weight it can draw. So I bought a bunch of springs to create like a traction testing rig or something. But yeah,
okay.
Yasha, you have some comments or thoughts on this? Like in a more ambitious world, where would you take this model to like do the dynamics testing?
Oh, the physical model?
Yep.
It really, I mean, there's all sorts of different, it depends on the test criteria. That would be the starting point for the selection of a test process that would then stress that particular test criteria, whether it be particular joint loading or otherwise. That could also be static, dynamic, or otherwise. Here, for this vehicle, presumably we're going off-road where there's a lot of vibration. And in that case, you would actually clamp this down to a table, which just violently shakes the thing. And that would be one way to kind of do an accelerated life test as one class of testing that you would perform.
But that's physical, right? I'm talking about like in CAD, like, well,
oh, the simulation.
Yeah, like how much some of the things I'm really interested in is since a rover goes over rocky terrain and it's going to have like shock loadings quite a bit, like one wheel kind of falls off a rock and like suddenly sharply impacts and the other wheel comes off. It's going to have a lot of impact loading unevenly. It's going to have vibration, like you said, but I think actually vibration may not be as much of a problem for rovers because they're typically slow vehicles. All these are going to move very slowly, but they are going to like fall in awkward angles and positions. Like one interesting test I'd like to do is just give it a particular geometry in simulation and then drop it from a height, just boom, and see how that shock loading actually affects which joints break and so forth. Because the very first thing a rover would do on Mars is literally be dropped on the surface, right? So
yeah, I mean, to speak to your vibration concern, this vehicle goes through an extremely harsh life with regards to vibration on the launch vehicle. So this is actually a very large concern, is if there's a particular element of the mechanical system, if perhaps it isn't fully constrained before it gets dropped off of the launch vehicle payload bay, there could be some vibrational mode which causes a structural failure. And this would be a concern. So you do need to run kind of a, harmonic kind of dynamic analysis of the entire structure to see if there's anything that'll shake itself at some particular vibrational mode. But
I remember there was one in the launch of Curiosity and Perseverance, the differential mechanism, actually, they built a very special rig just to hold it in place for the vibration of launch and descent. Like literally the differential bar and all the turnbuckle stuff was locked in place because that was like one of the most delicate weak spots. So you would probably have like a rigging to actually handle this for launch and descent.
And to your point, on Earth, we can have a much more sophisticated packaging system where like you buy the microwave and there's a bunch of stuff inside the microwave that's kind of like packaged up and can be pulled out and reassembled internally. Here, we don't have that luxury, so it must all be external and easily deployable throughout the mission. To speak to the question about simulation, though, Onshape does have a couple, so there's no native simulation capability, but I believe the most popular add-in is the SimScale FEA package, and that can run kind of in the Onshape environment. It's a meshless FEA package, which is kind of a new age, kind of a different way of doing these calculations. But it's a meshless solver that is included, or sorry, it's not included, but it's compatible. It's an add-in that can be run in the Onshape environment. Beyond that, though, like the industry standard is ANSYS. And for instance, to speak to the crash simulations for automotive, the really popular one there is Abacus, which I believe is a Dassault product. It's often used like in conjunction with CATIA if you're doing, like a Mercedes auto body or something.
So none of these really seem to have changed since I last looked into this. These are all really old packages. Is there like a second generation thing like Onshape for finite element stuff, or is it all like just the old incumbents continuing?
Autodesk has purchased a couple things. So the Fusion simulation is pretty powerful, and their whole push is for generative design, right? So the Fusion simulation, not only can you run a simulation, but you can define criteria and objectives to have the simulation evaluate, and then it can generatively and iteratively rerun. And so this is kind of a combined functionality that you can have in Fusion. You could take this model out of Onshape and bring it into Fusion and then run simulations should you desire.
Okay.
But I would say in terms of like new wave, that's probably the most new wave is Fusion's offering. But other than that, you are stuck with the old incumbents.
I think I used ANSYS very briefly, like 15, 20 years ago, like for like a couple of hours. But yeah, I know the theory of finite element stuff, like pen and paper classes that I had in the 90s, but I don't have much experience actually doing finite element based like simulation testing of forces and stuff. All right, so to continue, the one last thing I wanted to point out here is this ball joint. The CAD model I got from McMaster-Carr. So this is like another thing that's changed a lot since I learned this stuff in the 90s. Now there's like catalogs of stuff. The good engineering suppliers, you can just go download CAD models for any reasonably like good part. Like if you buy crappy Chinese knockoff parts of eBay or Amazon, you're not going to get CAD models easily. But anything you buy off like a site like McMaster-Carr in America, and there must be equivalents elsewhere, you'll get CAD models. And this one, I just imported it, shoved it in. It's not great. It's a ball joint, but it too has the ball joint constraint problem. It doesn't like tell you how much it can actually rotate. But this is what it looks like. And this one, there's like one revolute joint here. I should show this side one. Yeah, this is a standard part in the Onshape library. So standard nuts and bolts you can just insert. You don't have to like design or import. Standard nuts and bolts you can do. this is not a standard joint, so I imported from McMaster Car. Let's see what else. Oh yeah, this bolt over here, another standard one. It's just an M3 45mm long bolt. So, okay, let's stop this, and already I've mangled it, and it'll take me a while to get this reset correctly. But okay, that's my review of the mechanical build. So let me go back to my.
I had one question about the design approach.
Okay.
Architecturally, you'd mentioned that scavengeability is a design criteria that you're looking to think about a bit more, but there is quite a bit of wire routing within channels, which is a very, very challenging thing to scavenge and undo. So I was wondering why you chose to go with that approach as opposed to a wire duct or externally routed cabling.
So I might still end up doing that. Like, this is like a fairly ambitious thing to try and do. One is because this is such a sort of kinematically complex mechanism that's going to like get convoluted in all sorts of ways. Joints are going to move in different ways. The wire harness is going to get stressed and turned and twisted in all sorts of weird ways, maybe get pinched in joints. So I kind of wanted to like make it as integral to the structural frame as possible. And there's some comments I don't want to like put on a video recording that'll be public, since it has to do with like client stuff I learned on a gig. But yeah, there's reasons I want to put it in the structural part, but also to make it a research problem. Like, can we make the wire harness also modular, as in it plugs and unplugs with the mechanical components? So I'll actually get to that. One of my discussion items is wire harness. So I want to talk about the how we might actually do that in the future. But for now, yeah, you're right. It would be better and easier to do modularity if the cabling were external. Okay, so this is the basic design that we just reviewed on Onshape. Turnbuckle, we talked a little bit about sort of one of the critical bottleneck pieces of modeling. All right, now let's talk about wire harness, which is just the topic Yasha just brought up. All right, so this is an older sketch, but just to give you a very visual idea of what the basic wire harness problem is, the BeagleBone Blue takes a 2-pin JST-ZH, which is a 1.5mm pin separation connector for the motors, and between 4 to 6 pin JST-SH connectors for things like the quadrature sensors and the GPIO ports and things like that. And there's the 3-pin Futaba males for servos. So just so you have a visual again, let's go back. These are what I'm talking about. Yeah, actually go back to presentation mode. Yeah, so all these are basically JST, SH, and ZH. These are Futaba regular servos. There's USBs and stuff. Oops, going the wrong way. Wait, what am I doing? Okay, so those are from eBay and Amazon. I just bought like small packs of like these connectors. This one came with the motor. On the left picture, the bottom right one, it came with the N20 motor. So it's just a connector that plugs into the 6-pin connector. So 2 of those are for the motor and 4 are for the Hall effect quadrature sensor. So there's 6 wires coming out of that. On the left over there, you've got 2. So the 4 wire one towards the top, that needs to connect to 4 of the wires on the motor cable and go to the quadrature sensor. And then the 2-wire cable needs to connect to the other 2 wires and go to the motor connector. And on the right, you have the servo motor, which is a separate 3 conductor cable. Okay, and I think these might actually be long enough at a pinch to go all the way without extension, but I doubt it. I don't know. This is a really, really ugly diagram. I think I was asking several weeks ago, is there a good diagramming tool for wire harnesses? And apparently there isn't. So this is just me using like an iPad drawing tool. It's crappy, but the red cable is what I need to design. And here's where the modularity question that Yasha brought up comes up. So if you actually wanted a properly modular wire harness where the mechanical subassemblies can be like just unplugged and replugged and you could swap them around, then basically you should be able to like undo the mechanical mate and electrical mates at the same time. So just like when you undo the ball joint, you should also be able to just pull apart a plug and suddenly the whole wire harness comes apart from the left rocker bogie to the body, right? That's what you want to be able to do. So the thing I've marked question mark A is the connector between the rocker bogie mechanism and the main body. So that would end up being basically 9 conductors. So simplest solution would be 9 pins. B, at the other end, you have to break it out into 6 pieces. This is just for one drive unit, by the way. So 6 motor, 3 for servo. So 9 conductors just to control 2 motors for 1 drive unit. So times 4, there's 36 conductors coming into the BeagleBone Blue. And we'll talk a little bit more about other strategies, but if you wanted this particular configuration to be modular, you'd need that middle red cable to be basically a separate interconnect. And then it would basically come apart into 3 pieces. Drive units would come apart. So 4 drive units would just unplug mechanically and electrically. The linkage assembly would come apart as an interconnect middle mile, basically. And then the last mile towards the board would come apart as well. So this would be one way to do the wire harness. Like I already mentioned, route through hollow members, route around mechanical joints, protect from weather, shorts, mechanical stress, blah, blah, blah. Try and design for modular assembly. Future, yeah, I don't know enough about sort of the electrical and computer engineering part of it to think about how you might use it with a bus. But I imagine you can do it with just like a signal bus and then have a breakout board at the motor level. So a simple motor, 2 motor controller that controls both the motors, and all you send it are like serial signals. So maybe you can just do it like a couple of signal lines, a power line and ground. So maybe just 4 conductors will do it, maybe even 3. 1 signal line, power and ground. Maybe that's all you need. Maybe you don't even need power and ground if the drive units are being powered by a separate 12-volt line, which has its own, like, voltage converters. Maybe you just need the signal lines. I don't know. So there's huge number of possibilities which I'm not competent to get into. I want to do the simplest thing possible that'll actually work for my first build. And next year, I do want to explore all this because, again, in the consulting gig, I sort of vaguely alluded to, which I think you all know which one I'm talking about. This is a huge bottleneck. It's like this messy middle layer of the abstraction stack. Nobody likes. It's a mess in every industry I've seen. Nobody knows how to do it well. And it's a cost and time sink. Like the actual raw materials cost may not be high, but teams of engineers spend months and quarters, schedules slip, entire programs slip because wire harnesses are like poorly designed and messy and all over the place. So wire harnesses are actually a good research topic. Not for me, but one of the things I hope to attract by at least defining the problem well is attract a member to this team who'll actually take this on as like a research topic. But more, this was the actual first solution I thought of, just ribbon cable. And Yasha was laughing at me when I showed this, and he was actually saying you should just do like buses. But this was like my first extremely naive one. And I realized that these ribbon cables are like so thick, like even shoving them through my 1/2-inch aluminum pipe is a pain. So a bundle of like 9 loose wires is actually easier to thread than a ribbon cable. And this would have a different connector strategy. All right, the actual physical connectors. The 3 I'm considering, one is the most common hobby electronics ones, which is DuPont connectors, which look like that picture on the left. They come in like, 2, 3, 5, whatever. They're both cable to cable and cable to board type connectors. Kind of bulky, not the greatest, but relatively easy to crimp and assemble. In the middle, you have JST. These are JST PH, so 2.5 millimeters. So yet another. So JST is like a spec that has like 6 different physical types with different pin separations. So this is a box I happen to have. Both are annoying as hell to try and crimp. And the third solution is to simply butt solder all the individual conductors one by one. Unfortunately, that's not reversible. It's nowhere near modular. So I would like to do a connector strategy if possible, but if not, my fallback is just solder the whole thing. Crimping is a major Yak on its own. I assume some of you are much better at it than I am. I'm finding I really suck. This is like a basic generic crimping tool. On the right is one specifically for DuPont crimping. So I have JST and DuPont crimps here. I'm trying both. I really, really suck at it. So this is one of my DuPont crimps under magnification. And on the right is the chart that came with my crimping tool on the standards of a good crimp. So this is just lack of practice on my part, but this is my like both build bottleneck, knowledge bottleneck, and like skill bottleneck, like literally making these crimped connectors. It's a complete mess. And what high quality looks like is like light years away from where I am. And by the way, it tells you something that NASA has scary, scary standards for wire connection. So they have a whole separate manual for soldering. This is just crimped connectors, and they prefer crimped connectors because you don't have molten solder flowing through stranded wire. Creates like both mechanical and electrical problems. So for a lot of reasons, they prefer crimped connectors. I still haven't thought it through. But NASA has a 100-page manual just on doing crimped connection interconnects properly. And I was scared looking at their like precise standards. Like, look at this, how much strain it has to be able to handle, all that kind of stuff. It's worth just looking through this manual just to get an idea of just how stringent space assembly of wire harnesses is for things that are designed to go into space. Okay, so that was my wire harness section. Final fun section. I wanted to design and build my own wheels and tires. PLA is not a good material for traction surfaces because it's hard and slippery. It won't hold well on anything except carpet, so you need something softer. I thought of doing PETG with low density prints, but PETG is really hard to print and I still haven't figured out how to print it. And I wasn't expecting to be able to print TPU. I forget what TPU stands for. Trans something. Anyway, it's a rubber-like filament. And my initial prints were terrible, like on the left. But then I found some information online on how to do it right. Its basic trick is you have to slow the hell down. Like you have to go really, really slow when printing TPU and lay down layers very slowly. And a couple of other tricks, how much you retract the head and crap like that. But once you get that figured out, you get nice, clean prints without all these hairy strands coming off. So basically now I can design and print my own tires. And now that I can do that, I'll print PLA hubs, tires, mount them on, and I can do my own wheels. So this was like a little victory I didn't expect to have because I was thinking of going with just toy wheels that I could buy. But the standard ones I found weren't the right size. And the one in the design I showed you, that's, I think currently my design is about 50 millimeter wheels. But basically this gives me flexibility to do my own wheels of any size. Oh, I see Anurag just joined. You missed most of the good stuff.
Yeah, that's fine. I had an appointment in the morning.
Well, the recording will be there. But okay, so.
But what is the speed with which you print TPU?
TPU is about half to 1/3 the speed of PLA. Like I think I was going 18 millimeter per, or 18 millimeter per second. No, that sounds too much. Whatever. It's about 1/3 from 50 to 18. Yeah, that's basically it. Yeah, if you have a 3D printer, I recommend buying some TPU and playing with it because it also creates all sorts of fun soft parts. I'm planning to print a bunch of bumpers with it. I should mention the drone crowd seems to really like TPU because drones crash all the time and you want to like protect your drones. So they try to make all the connector plastic parts out of TPU. And you can vary the properties of TPU very easily by changing the density. So if you print at like 20% density, you get like really soft rubbery things. And if you print at say 70 to 80%, you'll get a very stiff rubber. Actually, let me find my print and bring it to show you.
So is TPU softer than PLA?
Yeah, it's much softer. Can you see? I can press it. Press it.
Yeah.
Yeah. So it's compliant. So this is, I think, printed at about 20%. So 20% is fairly soft. I think this is about what I would need for tires. But you can see it took a long time to get there.
So I have this PLA wheels, and then there is a outer covering you could as an optional. I could print that with the TPU.
I would recommend it if you're willing to do that experiment, because my suspicion is PLA, even if you print it at low density, it would just make it weak, like structurally weak. It won't actually give it the soft elasticity that'll make it a good tire. So but anyway, it's fun. It's a fun thing to experiment with, like just more materials. That's why, even though it was not strictly necessary, I made this composite plastic and aluminum design, just because I wanted to get experience integrating different materials together. So aluminum and plastic, I think, are the two kind of basic materials you need for most of these builds. Okay, so
Can you
next,
say something about the wheel design?
the
What I
wheel
mean,
design.
you put a lot of work into the mechanical design and explained the logic and reasons for it. How did you design the wheels themselves? Did you map them to a surface? Why did you choose TPU? I mean, obviously it's better than PLA, but is it more suitable? You know,
I mean, it's the only material available for 3D printing. It's the only 3D printable filament on like cheap low-end printers that'll create soft rubbery materials. The other options are, you could actually work with actual injection molded rubber and stuff, or you can buy rubber tires that come for hobby cars. Like there's a whole market on Amazon. If you search, you'll find like lots of rubber tires of different sizes that the RC monster truck people use, but it's like limited. Like they're you kind of, it's build or buy. So on the buy side, you're limited to toy car parts and hobby racing type things. On the build side, if you're 3D printing, TPU is pretty much your only option. If you wanted to, you could buy like stock rubber and like actually like, you know, cut it with a knife or something and like machine it that way. That'll give you a few more options of materials to work with. And if you wanted to go with like, so this is all Earth materials. None of this would work in space. Obviously, they would go brittle, and that's why they don't use rubber on Mars. So I don't want to go into like that right now, because like this is still Earth rovers, right? But if you wanted to do like moon lunar rover style, that's the wire mesh type weird tire. Mars rovers is like very thin aluminum stiff things. Yeah, all that is worth exploring as a sort of whole research topic in the future on its own.
There is a these days you can get a desktop injection molders. Have you heard about it?
Oh wow, okay, desktop injection molding is way farther than I hope to go. But yeah, I think
I would actually like to mention it's a very, very commonly used process. I've also done it many times, is casting of printed molds.
okay.
So if you do need to create your tire out of a different durometer material, for instance, or a particular color, let's say it has to also match a particular color, and it has to be a bulk color, it can't be a surface painted color, you can simply print the negative of that part, which is leveraging the additive that's quick turn, obviously, but then you just simply cast it. So there are a lot of casting materials, whether it be rubber or solid, transparent, like optically transparent. So there are lots of different things you can do with casting. And this is also very
cool.
frequently used for low volume prototypes, like high aesthetic prototypes as well.
Huh. I hadn't thought of casting. TPU is available in all colors. So if you just wanted colors, TPU would be good, but different material properties would be good. Like TPU is like rubber, but I haven't really tried doing too much with it. But imagine like real rubber or other like synthetics, they'd have better, especially temperature properties. So especially if you're trying to do a rover that'll live in the, you know, hot Death Valley desert and survive there, and you want it to behave like rubber, that might be tough, or like Antarctica or something like that. So I don't know if TPU can do any of those things. But yeah, so casting is another thing we could do. Okay. So wrapping up, next steps for Nature's Murder. So get some solution for the wire harness, enough to do the accessory before the fact build going, so I can do some programming and stuff. Do the basic tests of all electronics and computation on the simpler ABTF build. Work out the basics of the battery and power. designed the initial payload for NIM. So the design I showed you is just the basic base rover. So it doesn't have any sort of sensors. It doesn't have any payload to do anything. So that I have to like add at least something. Finalize and fabricate the main rover, including the final wire harness. Then hopefully by then I'll have proven the computation and electronics on the ABTF rover, and I can just sort of integrate them into NIM very easily. And stretch goal for 2021 is to actually get the software to the point where I can do a simple low-level maneuver automaton. Like, it has a vocabulary of moves it can do, like turn, go straight, all that kind of stuff. But I think I'll be lucky if by the end of the year I get it to like move on its own 5 inches and turn right and go another 5 inches. So I'll be happy if I get to that much. Research ideas. Initially, I thought in this cycle we should talk about our research ideas, but then I decided the build update was more important. But anyway, so these are all my research ideas that I'm interested in looking into. Some are obviously inspired by the build itself, so parametric design in simulation of rovers. So the design I showed you guys, you can vary it in all sorts of ways, like make the struts longer or shorter, make the wheels bigger or smaller. So it's like very open to experimentation. Deep dive into wire harnesses in extreme conditions. So that's, I think, an important research topic for next year. Materials we talked about for rubber. So not just for wheels and tires, structural materials like PLA is probably not good for like outdoor rovers. I'll switch to ABS if I'm doing outdoors because PLA, I think, goes soft or melts at a certain temperature. Beyond aluminum, steel, lots of things you could do. And there's some theory topics that I think Eric and I chatted about briefly that at some point I'd like to get to, but it seems in the distant future right now. Okay, so this is it for my build update. Any questions? I'll leave that there, since this is the picture I'm most proud of. All right. You can stop the recording now, I guess, and wrap up.